In our last example, we were approximating the square root of 3.9. And using a linear approximation, we got an approximation that was accurate to 3 decimal places. Now, in our next example, we're going to approximate the square root of 9.14. So just like before, I am going to use the function f of x equals the square root of x. But I can no longer use the a that I had used previously. Remember what we chose before. We were approximating the square root of 3.9, so I chose a point of tangency near 3.9 that I could take the square root of. So I chose 4. Square root of 4 is easy, right? Remember that. All right, so if you take a look at our graph that we were doing, here's the point of tangency from the previous example at 4, 2. And I'm trying to approximate x equals 9.14, the square root. So here is the actual value. In red, it's 3.023. That is the square root of 9.14. That's on the square root curve. Look at what happens when I use a point on the tangent line from the previous example. I get a square root of 9.14 is approximated to be 3.285. And if you compare those two y values, the only level of accuracy is to the ones place. They're completely off with respect to the decimal values. There's a huge gap, and you can physically see that gap between the tangent line and the actual curve. And the whole reason that there is that gap is because my point of tangency is too far away. So I really want to move that. I want to move my a value to a point that's closer. And look what happens to my tangent line. It moves the point that the approximation point, which is in blue, closer to a. Let's do that. I'm going to move it until I get to a equals 9. Square root of 9 is easy to calculate. And 9 is also very close to 9.14. So now my tangent line is flat against the curve near all of those x values. And at 4, there's a huge gap. So I wouldn't use this tangent line for any approximations near 4, but I am going to use it for approximations near 9.14. So let's get to work. All right, so I'm going to change. Let's go back to that example. All right, and this time the a will be equal to 9. So I calculate f of 9. Of course, that is going to be square root of 9, which is 3. So we're dealing with a point of tangency at 9, 3. Now I need the slope at x equals 9. So f prime of 9, and same square root function. So the derivative is 1 over 2 rad x, or 1 over 2 times the square root of 9. All right, so that's 1 over 2 times 3, or 1/6. Now I write my tangent line approximation. So L of x would be equal to the y value, which is 3, plus the slope, which is 1/6, times x minus 9. And there it is. All right, now I'm going to plug in this 9.14 to approximate the square root of 9.14. In other words, square root of 9.14 is approximately equal to L of 9.14. And then I calculate that. So that's 3 plus 1/6 times 9.14 minus 9. All right, so notice that where I placed it, where did I plug it in? I plugged it in here where the x is. All right, so that's the only place where the x occurs. It makes this super easy to evaluate. So 9.14, and I do this difference. Well, that difference is 14/100ths. So I'm going to write it like that. So 3 plus 1/6. I'm going to turn it into a fraction. What's 14 over 100? If I reduce that, that's 7 over 50. All right, do a little bit of math in my head. All right, that's 3 plus 7 over 300. If I get a common denominator, multiply numerator and denominator by 300. That's 900 over 300 plus 7 over 300, or 907 over 300. See, we can do that. That's pretty easy calculation. So this is my approximation of the square root of 9.14. All right. All right, so let's compare them. All right, so L of 9.14. All right, that was equal to 907 over 300. And put that on the calculator, which is 3.023. I'll go to 4 places. Okay, and then I put square root of 9.14 on the calculator. And that's also, so that would be about 3.0232. And if I compare place values, the ones, tenths, the hundredths, and the thousandths place, I have 3 decimal places of accuracy. That is pretty darn awesome for linear approximation. I'm so proud of myself. Okay, let's take a look at another example. All right. Oh, before we do that, let's talk about some error estimation. All right. So when we took a look at square root of 3.9, and we want to calculate that error, that gap between the actual function, f of 3.9, and our linear approximation, we simply do a subtraction to find the error. And we take the positive difference. That's why it's in absolute values. All right. So if I calculate that on the calculator, I get a difference which is about let me change that to black, 0.000, remember those 3 decimal places of accuracy, 1581. That's pretty darn accurate. It's exactly what we were looking for, those 3 decimal places of accuracy. Okay, and so the idea here is if you have that curve, do a little quick sketch, there is a gap. So if this was my square root, if this was y equals square root of x, that's my curve. And then I have this point, this tangent line. That doesn't look like it's right on the curve, but you know my meaning. And we're trying to approximate a value near x equals 4. So this was at 4. And we're picking a value that's at 3.9. There's going to be, the idea is that there is going to be this gap between these 2 values. There's a point here, there's a point here, and then there's a gap. That is that gap. That is the error gap. That's what the measurement is. And that's a pretty tight gap, okay? All right, one other thing about managing error. When you place a tangent line on your curve, we usually place it on the outside of the bowl shape, whatever the bowl shape is. We call this concave down, and that's a bowl that's upside down. We have a concave up region, which is a bowl which is face up. And the outside, you can see where we've placed these tangent lines. So this would be the outside of the bowl. So there it is. And at some point, the outside becomes the inside if I change my curvature. So this is the outside of the bowl now. And so you have to kind of think about that. So the interesting thing is this. It kind of tells us about whether our error is an over or an underestimate. Because if the tangent line lies above the curve, then that means the value that we're approximating will also be above the curve. It'll be more than the y value of the curve. So in a concave down situation, the tangent lines are above the curve, and that means that we have an overestimate. So overestimates occur when we have a concave, when the curve is concave down. We have an underestimate. Well, that's when the tangent line is under the curve, and that's in a concave up situation. Okay. All right, let's try some examples in the next video.